And oh, Konstantin Serenko is here. Okay. Hello, Konstantin. So now we have
Hello.
hello. We have all jury members are available and time. Yes, I can start. So I start. Good afternoon, ladies and gentlemen. My name is Alexander Sveshensov. I am the chair of the jury, and I would like to start our meeting concerning PhD defense of Mrs. Daria Gerasimova. Now I would like to address to the foreign participants. I'm sorry for inconvenience, but because some part of procedure will be in Ukrainian language. But however, the presentation and discussion will be in English, and you can take part in this. Добрий день. Шановні колеги, починаємо засідання разової спеціалізованої вченої ради Інституту радіофізики та електроніки імені Олександра Яковлевича Усикова НАН України з правом прийняття до розгляду та проведення захисту дисертації Герасимової Дарії Олександрівни на здобуття ступеня доктора філософії з галузі знань 10, природничі науки за спеціальністю 104, фізика та астрономія. Спеціалізовану вчену раду, утворену наказом Інституту радіофізики та електроніки імені Олександра Яковлевича Усикова НАН України, номер 29 від 22.12.23 року в такому складі. Голова ради – це я, доктор фізико-математичних наук, старший науковий співробітник, старший науковий співробітник відділу теорії дифракції і дифракційної електроніки Інституту радіофізики та електроніки імені Олександра Яковлевича Усикова НАН України Свеженцев Олександр Євгенович, члени ради, рецензенти, доктор фізико-математичних наук, старший науковий співробітник, завідувач лабораторії обчислюваної електродинаміки відділу теорії дифракції та дифракційної електроніки Інституту радіофізики та електроніки імені Олександра Усикова НАН України Стешенко Сергій Олександрович та кандидат фізико-математичних наук, старший науковий співробітник лабораторії математичної фізики, відділу статистичної радіофізики Інституту радіофізики імені Олександра Яковлевича Усикова НАН України Сіренко Костянтин Юрійович. Опоненти. Доктор фізико-математичних наук, старший дослідник, завідувач відділу теоретичної радіофізики Радіоастрономічного інституту НАН України Ячин Володимир Васильович.
Це я.
Та доктор технічних, дякую. Та доктор технічних наук, професор, завідувач відділу числових методів математичної фізики Інституту прикладних проблем механіки і математики імені Ярослава Степановича Підстригача НАН України Андрійчук Михайло Іванович. Усі члени ради присутні.
Доброго дня, це я.
Засідання є правоможним. Порядок денний. Захист дисертації Герасимової Дарії Олександрівни на здобуття ступеня доктора філософії з галузі знань 10, природничі науки за спеціальністю 104, фізика та астрономія. Тема дисертації. Diffraction radiation from dielectric silver and graphene circular nanowire configurations excited by modulated electron beam. Дифракційне випромінювання на структурах скруглих діелектричних металевих і графенових нанониток, що збуджуються модульованим потоком електронів. Наукові керівники, кандидат технічних наук, старший дослідник, старший науковий співробітник лабораторії мікро- і нанооптики відділу квазіоптики Інституту радіофізики та електроніки імені Олександра Усикова НАН України Духопельников Сергій Володимирович та доктор фізико-математичних наук, професор, головний науковий співробітник відділу радіофізики твердого тіла Інституту радіофізики та електроніки імені Олександра Усикова НАН України Черпак Микола Тимофійович. Відомості про здобувачку. Герасимова Дар'я Олександрівна, 1993 року народження, громадянка України. У 2019 році закінчила з відзнакою Харківський національний університет радіоелектроніки і здобула кваліфікацію, ступінь вищої освіти магістр, спеціальність метрологія та інформаційно-вимірювана техніка, освітня програма фотоніка та оптоінформатика. З 1.11.2019 по 31.10.23 навчалася в аспірантурі Інституту радіофізики та електроніки імені Ім.О.Я.УСИКОВА НАН України. Працює науковим співробітником лабораторії мікро- і нанооптики, відділу квазіоптики Інституту радіофізики та електроніки імені Ім.О.Я.УСИКОВА НАН України. Здобувачкою подано до спецради всі необхідні документи згідно діючого законодавства, а саме дисертація, академічна довідка про виконання освітньо-наукової програми, висновки наукових керівників, висновок про наукову новизну, теоретичне та практичне значення результатів дисертації, копії наукових публікацій, в яких висвітлено наукові результати дисертації. За погодженням зі здобувачкою захист дисертації відбуватиметься англійською мовою. Дар'я, the floor is yours. You have up to 20 minutes to present the main point of the dissertation. Please start.
Thank you. Thank you for introduction. We'll share my screen. Do you see my screen?
Yes, and please
Yeah,
check.
or-
Please check in advance if you can switch slides. Please check.
Yeah, I think.
Just switch slides.
Yep.
Oh,
It
okay.
is
It works.
okay.
Okay, Дар'я, you can start.
Thank you. Доброго дня, шановні колеги та члени спеціалізованої ради. Hello, dear jury members and colleagues. My name is Daria. I'd like to present my dissertation work titled as Diffraction Radiation from the Electric, Silver, and Graphene Circular Nanowire Configurations, excited by modulated electron beam. My advisors are Dr. Serhiy Dukhopelnikov and Professor Mykola Cherpak. The following are my co-authored scientific publications. The 6 papers were published in the international scientific journals of the first and second quarters. In addition, research results were presented at 19 international conferences. Worth noticing, all papers are indexed in Scopus. The complete list of participated scientific projects is shown on this slide. Among them are both planned and competitive ones. Part of the work was carried out within the framework of National Research Foundation of Ukraine project. The contents of the work divided into an introduction and 5 chapters with conclusions, as is shown on this slide. Let me start with research goal description. The goal of the work is analysis of diffraction radiation resonance effect for various structures of circular nanowires and nanotubes made of dielectric, noble metal, and graphene, which are excited by harmonically modulated electron beam. The diffraction radiation is the radiation of electromagnetic waves of any frequency which accompanies a beam of electrons falling near metal and dielectric objects without touching them. To achieve the goal, the following tasks were set. First one, build a 2-dimensional mathematical model for the scattering and absorption of electron beam field from arbitrary ensemble composed of finite number of circular nanowires or nanotubes. Then develop a numerical algorithm for calculations of defined characteristics. Afterward, investigate how the resonances on the modes of various materials influence the diffraction radiation of a modulated electron beam. Next, establish a relationship between the scattering and absorption characteristics for the beam case. Then calculate the diffraction radiation problem with commercial codes to validate the theoretical results. And last but not the least, a study of eigenmodes of dimer made of nanowires and quantify the threshold conditions for the generation of these modes in the presence of active regions. This slide contains the object and subject study formulation. They are aligned to the goal. The first chapter of the dissertation consists of literature review and basic principle explanations. On this slide, I will explain the initial motivation for the research. It is connected to the task of non-invasive monitoring of charged particle beam position. The beam position monitors, or BPM, can be found in every accelerator. Its role to provide the information of the position of the beam in the vacuum drift pipe of chamber. In the Linux or colliders, the BPMs are used to measure the beam trajectory. For example, in microwaves, as it's shown on these pictures, the coaxial resonator beam position monitor explores the fact that off-centered beam excites the dipole mode TM110 in the cavity, with amplitude linearly dependent on the beam displacement. So in our study, the aim is to explore the opportunity of nanoscale resonator beam position monitors. For this, we introduce the following problem formulation. Here we consider a flat beam of electrons flying in the parallel to the x-axis at the distance h. The beam is assumed zero thickness and infinite in the z direction. Its velocity is fixed, which equals beta times c, where c is the light velocity and beta is the relative velocity of the beam and beta less than 1. Charge density function are presented below, and the incident beam's field is shown over here, and it is slow in harmonic. Note that this field is antisymmetric with respect to trajectory and decreases exponentially of the trajectory. All in all, this is a full wave two-dimensional boundary value problem for the Helmholtz differential equation in partial derivatives with exact boundary conditions plus the condition of local power finiteness and the radiation condition at infinity. The total field is presented over here and its components described on the right. After all necessary transformations, we get block infinite matrix equation as presented over here. And it can be solved numerically with controlled accuracy. Next, I will present and explain the main stages of the research. In the second chapter, configurations of the electric materials are considered. At first, for the beam position monitor model, we choose the dimer configuration of identical dielectric Filco nanowires. Since we have two wires, then the modes of such a structure are so-called supermodes, built on the natural modes of each individual Filco wire and optically coupled in four possible ways through two-fold symmetry. Here, the total scattering cross-section in visible range for several values of relative velocity of the beam is presented. On the right, its zoom is shown, where one can see the appearance of new resonances when the beam is shifted. Below, the near and far field magnetic patterns are present. The center pattern shows the field in the new resonance, where the intensity difference in two wires can be observed. This very phenomenon can be used as a physical basis for the beam position monitor. However, for dielectric materials, even with a high dielectric permittivity of about 12, it is difficult to achieve high Q factors without increasing the size of the wires. Therefore, for the use of truly nanoscale wires, it is necessary to choose another material. Such materials can be noble metals. We choose silver due to its localized surface plasmons and moderate losses compared to the other materials. And this study is shown in the chapter 3. To describe the dielectric permittivity of silver, we use the experimental data of Johnson and Christie, which are depicted on this slide. As one can see, there are two remarkable wavelengths, both line and ultraviolet. One is around 306 nanometers, where the real part of epsilon is close to 1. This means that the silver is optically well transparent at this wavelength. Also, the losses remain significant, as the imaginary part almost 2. We stress that this effect of quasi-invisibility cannot be reproduced with the Drude formula for the electric function of silver. This justifies our choice of experimental data in the analysis of silver scatteral in the visible range. The another important wavelength is 337 nanometers, where the real part of epsilon equals -1. This is the approximate quasi-static textbook value for the collective resonance on the localized surface plasmon modes of the singular circular metal wire in the free space. And it is valid if the losses can be neglected, when the imaginary part is close to 0. Using this data, we compute the normalized scattering and absorption cross-sections for the dimer of silver nanotubes, nanowires excited by electron beam. Natural modes of silver dimer are similar to dielectric ones. They form so-called plasmon supermodes built on optically coupled localized surface plasmon modes of each wire. The effect of quasi-invisibility is presented for the plots of total scattering cross-section for the thin and for the thick wires. The associated minimum is especially deep for the thicker wire. On the plots of absorption cross-section, there is no similar minima due to the considerable losses in the bulk silver. The resonance near magnetic field are shown as well. So, in contrast to the high reflective index dielectric dimer, the low values of localized surface plasmon mode Q factors and their clustering near the same wavelengths show that the solid circular metal wires are not the optimum choice for the application related to the optical beam position monitors. To overcome these negative factors, one can either take wires of non-circular shape or use circular silver nanotubes with thin walls, as we did in the next investigation. On this slide, we present a similar problem for the dimer of silver nanotubes. The visible light spectra of partial scattering cross-sections for the several electron beam velocities is presented on the left. In such dual structure, the modes are also supermodes. Moreover, the modes of silver nanotubes are hybrid. They are formed at sums and differences of plasmon modes of the inner and outer surface of the tube. The near fields of resonance are given below. Additionally, since silver has considerable losses in the visible range, the absorption spectra of such structure are presented on the right, where the comparison with the results of similar calculation by the commercial code is made. Below, we present the reliefs of the scattering left and absorption right spectra dependent on the thickness of the nanotube wall. As one can see, now the observed nanotube resonance peaks are well separated in frequency for the different azimuthal orders and have higher Q factors. Further, using the acquired knowledge and deciding to use the thinnest existing nanotube as a basis for beam position monitor, we conclude that the graphene layer wrapped around the dielectric nanowire, or namely a graphene nanotube filled with dielectric, is well suited for this purpose. Such configurations with graphene are described in the chapter 4. The most widely adopted today model of electron mobility in the graphene monolayer is Kubo formalism. Here the graphene thickness is considered 0 and its surface conductivity depends on the cyclic frequency, chemical potential, electron relaxation time, and temperature. This value consists of two contributions, which are intra and interband conductivities, both presented below. Then the normalized surface impedance of graphene is that, which is shown over here. And using the Cobo model, it is possible to derive approximate expressions for the frequencies and Q factors of the plasmon modes of the single nanowire. These formulas allows us to estimate the range where the resonances will appear. This slide deals with the diffraction radiation problem of dimer of circular graphene nanotubes with dielectric filling. We show the spectral scattering and absorption cross-section of such structure for two values of chemical potential mu. The pictures for the bigger mu has no more noticeable new resonances, and the near field patterns in marked resonances for the case of shifted beam is shown below. The upper panels corresponds to the field magnitude patterns. The lower panels corresponds to the field phase patterns. And to sum up, this analysis showed that such a dimer serves as an infrared beam position sensor. The next step was to study the diffraction radiation of finite lattice of graphene-colored nanowires. In addition to beam position monitor, such structure can be used as the elements of the electric laser accelerators. This slide shows the investigated configurations. For the twin inline structure, the distance between the wires is small, so the scattering and absorption cross-section below display a split of plasmon modes, as in previous cases. For the lattice of a large number of nanowires, for example, 100 wrapped in graphene, in addition to plasmon modes at 313 terahertz, the lattice mode around 300 terahertz appears on the plot. This happened due to the period of gradient equals to the one modulation wavelength of the beam. Here, the plasmon supermodes of different symmetries merge completely into one resonance, precisely because of the much larger distance between the neighboring wires. Meanwhile, the intensity of the lattice resonance depends on the number of the nanowires in the gradient M. Overall, this study can be useful in the design of section of the electric laser accelerator. And in the last chapter, the threshold conditions of the plasmon modes of the dimer made of circular nanowires covered with graphene were studied as a model of nanolaser where the resonator is formed by graphene nanotubes and the tubes are filled in with gain medium. As follows from the Poisson's theorem, arbitrarily passive open resonator eigenfrequencies can be only complex with non-zero imaginary part that corresponds to finite radiation losses. Therefore, in order to emit the electromagnetic wave, this, which does not attenuate in time, an open resonator must contain an active region filled in with the gain material. Within macroscopic electromagnetics, these properties are translated to the negative losses, which are expressed by the corresponding sign of the imaginary part of the dielectric constant and reflective index. Our instrument is Lasian eigenvalue problem or LAP approach, which has been already applied to the several types of microlasers. We consider the complex dielectric permittivity and reflective index as shown over here, where the alpha is known reflective index and gamma is unknown threshold gain index. Within the lab, we look for the frequencies and the gain index thresholds of the laser modes as eigenvalue pairs. As a result, we get a matrix equation of the following form. This is a determinant equation generated by the second kind Fredholm matrix for each of 4 classes of symmetry. And to illustrate the splitting of dimer plasmon supermodes into quartets, the near magnetic field patterns for 4 symmetries are shown on the center. And additionally, an approximate expressions for the transverse plasmon mode frequency K and the threshold value of the gain index gamma for the closed graphene shell are given over here. Interestingly, frequently used in laser physics quantity of product of K and gamma, which is the gain per wavelength, that does not depend on the wire radius, chemical potential of graphene, and mode index in considered approximation. Therefore, within this approximation, all plasmon modes under any variation of this parameter stay at same hyperbolic trajectory, which denoted here under the supermode trajectories for the varied chemical potential. And this trajectory is controlled only by electron relaxation time and the wire reflective index. Below, one can see the trajectories of the dimer plasmon supermodes quartets under the variation of separation distance between the wires. It can be seen then when the distance increases, all supermodes approach to the threshold and frequency values of the single wire marked with asterisks of different color. At the end, we have following conclusions. If the beam trajectory is shifted from the central position, then the scattering and absorption spectra display appearance of previously absent resonances. The intensity of new peaks are proportional to the beam displacement. Then the above-mentioned effect has been found for the high-Q supermodes of the dimer of high reflective index dielectric wire, thin noble metal nanotubes, and graphene-covered wires at high enough values of chemical potential of graphene. Then in the analysis of sparse finite periodic array of many graphene-covered nanowires, the dominant feature in the frequency spectra are the resonances on the plasmon modes of each wire and the lattice modes of whole array. Afterward, the optical theorem has been adapted to the diffraction radiation effect of the modulated electron beam. Also, in analysis of the threshold conditions for the plasmon modes of nano laser based on the dimer of 2 graphene nanotubes filled by gain material was carried out. It is shown that one supermode of the dimer has a threshold lower than that of the single nanotube. And last, the developed computational codes of the scattering and absorption characteristic permits using them as a core of software for the numerical optimization of optical configurations, key elements of which are circular nanowires. So thank you for your interest.
Thank you for your presentation. Please ask questions. Are there any questions?
Yes, of
Okay.
course.
Please, Volodymyr, start.
Dasha, explain, please, term supermode. What does it mean? I think that it's slide number 9.
So, thank you for the question. Yeah. The supermodes, it's the modes which are built on the natural modes of each of the wire. We have 2 wires, and they are optically coupled for possible ways through two-fold symmetry. So for the one wire, the modes for our beam is degenerate and the antisymmetric. And if we have 2 wires, they are coupled, so they will be 4 of our supermodes. And for example, On the last slide with the laser problem, we see that all these symmetries are different by the nodes of eigen, odd eigen, eigen odd, and odd odd, with the name of the line of symmetries to the x and y axis. I hope I answered the question.
Okay, thank you. Are you satisfied with the answers, Volodymyr? Volodymyr, are you satisfied?
I think he's
Volodymyr,
lost.
I'm addressing you. We cannot hear you. Okay, who else wants to ask something? Please. No questions?
May I ask a
Yes,
small question?
Yes, please.
Daria, what programming language was used to write the codes?
We used open source Scilab program. It is similar to MATLAB, so it was write as the code of kind of MATLAB code.
I see. Was it part of your work on the dissertation to write the programs, or it was done by someone else?
No, all the programs was written by me and with help by my advisor, and I didn't give it I don't know. I didn't mark it as the part of the work. It was like something we use to solve the problems. Oh yeah.
I see. Thank you.
Okay.
Thank you.
Who else wants to ask something? Please.
I have a minor question regarding slide 13.
Yes, please.
This is Andrzej Szczepkowicz.
Yeah, thank you.
Was it 13 or was it a neighboring slide? But you mentioned a single nanowire, right? So what do you mean by a single nanowire?
I hope I understand the question. It's about these formulas of plasmon frequency and key factors for the single nanowire, but not just a nanowire. It is dielectric nanowire covered with graphene, as in our next problem here. Two nanowires covered with graphene, and these formulas are the approximate expressions for the one wire. If we have such problem with one wire, that these equations allow us to calculate the frequency of our near plasmon resonances and their Q factors.
I'm more trying to understand what is the structure. So if I understand you correctly,
it's a
nanotube or graphene nanotube, like it goes
yes,
around.
We can neglect this one, and it will be one wire problem.
Okay.
Of graphene nanotube filled with dielectric.
Okay, I see. Thank you.
Thank you.
Daria, I have some questions to you.
Yeah, please.
Could you show me the integral equation in your first part of scattering problem? Integral. You reduced your problem to the integral equation. Yeah. No. It's
this
not
one.
It's not integral. It's a okay.
Matrix.
Yes. Infinite matrix equation. Okay. My question is is the element of regularization in your approach? Did you do something? How did you obtain this equation? You did some regularization, or what did you do? Because it's a second kind equation.
Yes.
And what is the sense of your regularization? Please explain. What does it implies?
Mhm. Okay.
Right.
Thank you for question. As I understand, yeah, this equation which we got at the final, we transform our equations to the form called Fredholm's second kind form equations, which means regularization. We did regularization by using the wave factor, this one which is asymptotic of the Bessel function for the big index. And it was done not by us. We use the knowledge from previous researchers, for example, Solhub, who did this with the wave factor in which was a Bessel function, but it has some drawbacks, and in our problem we use some such approximation, not such approximation, asymptotic, yeah, for Bessel function, to avoid some zeros in the calculation. So, if I hope I answered the question.
Mm-hmm. Okay, thank you very much. And my
Thank you.
second question is, you in your dissertation you are using excitation by the electron beam. Your structure is excited by the electron beam, but a lot of researchers, they use just plane wave excitation. What is the principal difference, plane wave excitation and your choice, beam excitation, electronic beam? What's the principle? Is there a difference?
Yep, thank you. Yeah, they are different. As actually, they have three differences. The plane wave amplitude is constant. In our problem, the beam field decreases exponentially of the trajectory, and it is the so-called surface wave. The next one is plane wave field is symmetric with respect to any line along the propagating direction, while the beam field is antisymmetric with respect to the beam's trajectory. And the third one, it can be described as the beam velocity is the beta times t, as it's shown over here. So the beam is so-called slow plane wave or slow wave. This beta times c is less than the plane wave phase velocity. So yeah, I hope I answered.
Okay, thank you very much.
Yes, thank you.
Who else wants to ask something, please?
Yes, I have
Yes,
the question.
Your turn.
Yes,
I ask you, did you satisfy by the previous answer? You didn't answer you.
Yes, of course, I completely.
Okay, please ask.
Dasha, you compared your data with commercial code. What kind of code? What kind of code?
Yeah, maybe it was a little bit fast, but
I mean DFTD or finite element method.
It was console. I think it's DFTD method in basis. Yeah, it's here. with squares and circles, which is calculations compared to the other curves. FTD, yep.
Okay, and I think it was free of charge.
No, we did it a long time ago with our colleagues where you now at RAN. In RAN, yeah, colleagues from RAN.
Okay,
They
thank
gave
you.
us
Thank you.
permission. Thank you.
Okay, in addition to this question, I would ask also, in this commercial software, your structure was two-dimensional or three-dimensional?
Two-dimensional.
Also two-dimensional, yeah? Not
Yep.
three. Mhm.
No.
Okay, thank you very much. Who else
you.
wants to ask something?
May I ask a question?
Yes, yes, of course.
Daria, congratulations. That was a very well presentation. But as I understood from your beginning at the page of 1, your eliminated your excitation is completely related with the Z component of the magnetic field intensity. Is it right?
Yep. Yes.
In here, and at the end of your presentation, I saw from graphics that only the cross sections, but I wondered that what is the other polarization types? For example, what happens when these fields scattered from this structure, especially in terms of the electrical field intensity?
We didn't investigate the electrical fields due to, in our problems, we primarily concentrated on the plasmon modes. So yeah, I cannot, I think, answer right now for this question.
So I understood in here that you didn't work with the vectorial field, right? Did you work on the scalar field? Because I guess I saw from the beginning of your excitation field is the Z magnetic field component, Z component of the magnetic field of the beam. You know, the beam
Yeah.
includes
Yes.
both of the electrical field and the magnetic field. So you just consider the Z component of the magnetic field. Therefore, it can be better to speak. We just consider the static field, not the vectorial fields. These are right.
Okay.
Illumination.
I agree.
Incident field is beam field. The incident beam field is taken as the Z component of the magnetic field, right? So your illuminated is a vector. Therefore, I wondered that what happens when you eliminated this beam, to the related rods, and after the scattering from these rods, what happens to the electrical field intensities or the other components of the magnetic fields?
Okay. I can try to learn this question in details, and we can talk about this again.
Okay.
Thank you.
Okay, no questions? Who else?
I have one short question.
Can I question?
Yes, please.
You have used delta distribution in y direction for your charge density function. And my question, do you expect any differences, some differences if you use the distributed density function in y direction? Is it a principle? Is it important using of delta function in charge density function?
Yeah, Thank you for the question. We used it to present our field as a plain sheet of current to simplify our incident field. So yeah, I think it is important.
Thank you.
I hope. Yeah, thank you very much.
Who else wants to ask something?
I have some short question. Good?
Yes. Please,
You're
yeah.
welcome.
Excuse me, please, for such non-understanding. I understand that you use some commercial software, and do you have some problem with exactness of calculation? Because your characteristics are very sharp, and it may be the problem of software, and it, how you can say about this situation? As example, was this fig in?
Yeah, it was not widely investigation. We get such comparison only for absorption, and the commercial code is managed all our such parameters. It was a little longer than our calculations, but yeah, as you see, they are overlap very well. Yep.
Are you satisfied, Professor Andreychuk?
Okay, thank you.
Thank you.
Okay, thanks. I suppose we can close asking questions, and we will go to the next step. We should move to the discussion of the thesis. I'm giving the floor to the first external reviewer, Dr. Vladimir Yachin, please.
Okay. Good afternoon, dear colleagues. Because I speak first, I will give my review in details according to the requirement of the Ministry of Education and Science of Ukraine for opponent's review, and of course I renew some aspects of dissertation in your memory. Let me start. Microwave range diffraction radiation is already used as a convenient method of non-invasive diagnostic of beam in accelerators, which are commonly referred to as a beam position monitors. Today, the development of beam position monitor can be extended to the optical range because the emergence and rapid development of nanotechnology opens the way to create ensembles of nano-sized optical sketch arrays with controlled shape and locations. Nanoscale components introduce very little perturbation to the beam, its velocity and trajectory, and therefore its field can be considered fixed. Therefore, the analysis of diffraction radiation effect of beam of charged particle moving near nanoscale obstacles is necessary and inefficiently covered in the available scientific works. Hence, the subject of research of the Darya Gerasimova's dissertation is the resonance and spectral characteristic of electromagnetic field scattering and absorption by finite configuration circular nanowires and nanotubes excited by the modulated beam of charged particles, as well as eigenmodels of such nanowire configurations. The relevance of the topic of Darya Gerasimova's dissertation is linked with fundamental research in the field of nanophotonics and optics, and the additional practical interest of application in the field of radiophysics, namely the study of phenomena of the scattering and absorption of the modulated electron beam field by dimer configurations of the electric silver and coated with graphene as beam position monitors and finite gradient of such wires as the electric laser accelerator is relevant. The goal of this work is to analyze the diffraction radiation effects for various structures of circular nanowires and nanotubes made of dielectric metal and graphene for choosing the configuration which are the most sensitive to variation in the trajectory of beam and to the changes in its velocity. To achieve these goals, the following tasks are solved: building adequate two-dimensional mathematical models of investigated configurations, developing corresponding numerical algorithms for computation of the scattering and absorption characteristic, as well as the field in the near and the far zones of studied structures. The influence of different types of resonances on the diffraction radiation of a modulated electron beam was investigated. Optical theorem was modified for modulated electron beam case. The theoretical result was confirmed by the use of the commercial numerical codes. Recommendations for optimal design of the optical beam position monitor were made. Structure of the dissertation of Darya Gerasimova consists of an abstract and introduction, 5 chapters, general conclusions, list of used sources, and appendix. The dissertation work based on the 6 journal papers that was published in the international scientific editions and 19 conference papers in the proceeding of international conferences. The first chapter deals with the basic method of analysis of wave sketching by circular configurations of dielectric wires, the presentation of the incident field as a harmonically modulated field of beam of charged particles, the complex permittivity of silver and as a function of frequency. The description of graphene conductivity using the Cubo formalism, sketching and absorption of the characteristic representation, and the description of optical theorem adapted to the beam field, and the formulation of the eigenvalue laser problem. In the second chapter, the sketching problem is formulated for finite number of circular nanowires excited by modulated electron beam. Also, the chapter is devoted to the numerical study of the scattering and absorption characteristic in the visible range for single dielectric nanowire and dimer of 2 such nanowires. The third chapter contains an analysis of scattering and absorption characteristics for single circular silver nanowire and dimer configuration of silver nanowires and nanotubes in the visible range. In addition, this section provides a comparison of the absorption characteristic of the silver tubes dimer with result of commercial solver. The fourth chapter numerically investigates the scattering and absorption characteristics in the terahertz range for single graphene-coated circular dielectric nanowire, a diamond configuration of such graphene-coated nanowires, and finite array of graphene-coated circular dielectric nanowires. The fifth chapter presents the implementation of the laser eigenvalues problem approach for study of the electromagnetic field in the presence of one circular quantum wire, which is made of a gain material and wrapped in graphene and the diameter of 2 identical such wires as the threshold of stationary radiation. At the end of each chapter of the dissertation, the author gives relevant conclusions. Overall results are given at the end of the work. Therefore, the personal contribution of the PhD student is decisive. In my opinion, the presented research results are correct and reliable. This is confirmed by the use of well-known and reliable research publications in rating professional international journals, which are included in international multidisciplinary databases. The results presented in the work have been successfully tested at an international scientific conference in Ukraine and abroad. Therefore, there is no doubt about the validity of scientific statements, conclusions, and recommendations formulated by the applicant. Among the number of new results obtained, the significant ones are the following. The effects of resonant response in the diffraction radiation of modulated beam of electrons of high refractive index dielectric wires, thin noble metal nanotubes, and graphene covered wires at the high enough values of graphene's chemical potential was revealed. The results of numerical analysis of diffraction radiation caused scattering and absorption characteristics versus the frequency and other parameters. The far and near field pattern of the wave emission from charged particles being moving near various nanowire sketches and gratings of them were obtained. They have fundamental significance and wide range of application, including the beam position monitor and dielectric laser accelerator designs. The analysis of threshold conditions for the plasmon modes of the considered in this thesis, nanolasers can help in the creation of new, more efficient sources of waves. The optical theorem has been adapted to the diffraction radiation effects of modulated electron beam. Among the questions and comments on the content of the work which are worth discussing, it's necessary to note the following imperfections. In my opinion, it was worth analyzing in more details the effectiveness of monitoring the position of the beam with round bars made of different material and configuration. Additionally, provide a graphical comparison. There are few comparisons with simulation results in commercial applications. It would be necessary to provide a comparison of theoretical data with experiment. The author should not have used the term near field to the distribution of the field inside the cylindrical object. This is the internal field of the object. The work does not analyze the influence of angular displacement of trajectory of the modulated beam of charged particle on the diffraction radiation. In the last chapter for the study of grating made of dielectric nanowires covered by graphene, the absorption characteristics are not presented. The shortcomings should also include the presence of stylistic and typographical errors in the text. Worth noticing that the above-mentioned shortcomings are not of a fundamental nature and do not affect the overall positive assessment of the work. I believe that dissertation work of Darya Gerasimova completes itself prepared, qualifying scientific study in which new scientifically based and particularly valuable results were obtained. The main advantages of this dissertation work include the fact that all the results obtained by the author were published and appropriated in a highly rated international journals and conferences. I am convinced that according to the relevance, novelty, scientific level, and scope of the conducted research, the dissertation of Darya Gerasimova, entitled Diffraction Radiation from Dielectric Silver and Graphene circular nanowire configuration excited by modulated electron beam meets the requirement of Ministry of Education and Science of Ukraine, which are submitted to the works submitted for obtaining the scientific degree of Doctor of Philosophy. In particular, clauses 9, 10, 11, 12 of the temporary procedure for awarding the degree of Doctor of Philosophy, approved by the decree of the Cabinet Ministers of Ukraine dated March 6, 2019, number 167, with changes according to the decree of the Cabinet Minister number 608, dated September 6, 2021, and its author, Daria Gerasimova, deserves to be awarded the degree of Doctor of Philosophy in specialty 104, Physics and Astronomy, 10 Natural Sciences. I've done. Thank you for attention.
Okay. Thank you very much. Especially I like in your response that you appealed to some articles, to some articles. Yeah, detail. Thank you, Daria. Please respond to Dr. Yachin's remarks.
Thank you for your feedback, Dr. Yachin. I totally agree with your remarks. And regarding angular displacement, I can say that I had certain investigation, but it gives similar results to the vertical displacement of the beam, so I didn't include it to the already large dissertation. And I think it was in my conference paper in 2020. Yeah. And regarding, I think, the absorption characteristics, which are not presented for the gradient, yeah. This was done because of the lack of time in preparing dissertation. The research was almost in the end of the year where the dissertation was finished. So thank you very much.
Okay. I'm completely satisfied.
Thank you, Daria. Excuse me, Daria, but in some plots I saw absorption, scattering, absorption, cross-section for graphene. Yeah. I saw this. Why
no graphene, gratin.
It's not graphene.
Gratin with many nanowires. The last results about the graphene. Yeah.
Okay, thank you very much. Okay, we can next step. Next, the floor is provided to the second external reviewer, Professor Mikhailo Andreychuk. Please start.
Good afternoon, Mr. Chairman. Good afternoon, the members of Council. You are hearing me good?
Yes, very good.
So, I asked to not speak about content of dissertation because Daria said very good this content, and I want to say about the items concerning the only evaluation.
We lost connection a little bit. Oh.
Instances and the validity of reliability of the scientific results, conclusions, and recommendation presented in the dissertation work are achieved by using the justificate method of solving the problems on a set of non-science bodies and through multi-facet system virus use result of numerical modeling, and the novelty of scientific statements and results. The author obtained a series of new scientific and practical results, among which, in my opinion, the most important are the following. The first one, it is substantiated that the beam trajectory is shifted from the center symmetric position between the twin nanovirus, the diffraction, radiation, scattering, and absorption spectra demonstrated the appearance of previously unknown resonances associated with the dimer supermodel where the fields are orthogonal and the intensities of new peaks are proportional of the beam displacement or its angular shift. It is very important because has some practical application. The second one is the process of the diffraction radiation analysis for the sphere finite periodic arrays of many graphene-covered nanoviruses. It is shown by computation that the domain feature of the frequency spectra of diffraction radiation power defines the resonances on the plasmon models of each wire and the lattice models of the array. And the second item of novelty is analysis of the lasing threshold condition on the models of single circular graphene-covered active wire. Author substantiated the wire radius larger than 10 micrometers than the parasitic dielectric wire models are not weaker than the working plasmon models relatively to the frequencies and in the threshold values of the gain. The above is important information for the practical implementation of the corresponding arrays. And the practical work of the obtained results. The practical significance of the obtained results lies in the possibility to use the results of numerical modeling for the development of plasmonic graphene nanolasers. And developing software for studying the scattering absorption characteristics of the nano arrays can be used as platform for numerical optimization of optical devices, key elements of which are circular nanowires. And the main results of the dissertation have been published in 25 scientific works. 6 of them are very prestigious publication in a journal belonging to Q1, Q2 quartiles. And approbation of result is very impressive because we have the presentation on the European microwave conferences several times in IEEE International Conference on Microwave Communication Antennas on Electronic System, European Conference on Antennas and Propagation, also several times, and IEEE MTT National Microwave Symposium one time. And remarks. The second one, in page 9, annotation in Ukraine, the first item of the scientific novelty that headline the word "відсутні" must be replaced by "невідомі." And the next remarks follow from the previous because in page 22, in the first item of the scientific novelty, headline the word "absent" is used incorrectly, must be used "unknown." Instead of, because it is very important. Absent and unknown, it is very different words. And third remark is, in the last item of the scientific novelty, page 23, the second paragraph below, where is said about the threshold of supermodels for the stand-alone and set of areas, it is declared that the threshold values can be differ, but this is not demonstrated convincingly by the numerical simulation. And next remark, the numerical results are widely presented, but the quality of figures requires the higher resolution because the quantitative assessment of the radiation characteristic is inconvenient. This concerto figure in chapter 2 and in chapter 3 as well. In page 67-68, it is said about the optical theorem has been satisfied in the level of machine precision. and boundary conditions have been satisfied with the same accuracy as the solution of the matrix equation 2.36. But there are no numerical data concerning this evaluation. In my opinion, such numerical data would be a strong confirmation of the analytical statement that related to this provision. And summarizing this remark, only should note that the above remark related to drawback of the dissertation do not affect the overall positive assessment of the completed research. They do not reduce the scientific knowledge and practical worth of the dissertation work, and do not reduce the overall positive assessment of the conducted investigation. And final conclusion. PhD dissertation, the fractional radiation from the electric, silver, and graphene circular non-wire configuration is guided by modulated electron beams authored by Daria Gerasimova, is written in modern scientific and technical language, consistently, logically, and complementarily. The style of presentation of materials ensures the accessibility of its perception. Dissertation work is, in terms of content, is a complete scientific study containing new scientifically based results that are important at the current state of studying the scattering characteristic of the nanovirus and arrays consisting of such nanovirus. And it corresponds to the field of investigation in the specialty 104, physics and astronomy. This scientific work of the dissertation is undoubted because the result of research are published in 6 papers of the journals which belong to two parties. In terms of scientific level, practical work, approbation and publication, the dissertation meets the requirements set for in the decree of the Ministry of Education and Science of Ukraine on January 11, 2017, number 40, on approval of requirements to the seat of dissertation, and also meets the requirements stipulated in item 10 of the procedure for conducting the experiments on awarding the degree of Doctor of Philosophy and approved by decree of the Cabinet of Ministers of Ukraine on March 6, 2019, number 167, on conducting the experimental and awarding the degree of Doctor of Philosophy, and its author, Daria Gerasimova, deserves to be awarded with the scientific degree of Doctor of Philosophy in the field of knowledge 10, natural science, which specialty 104, physics and astronomy. Thank you very much for your attention.
Thank you very much, Professor Andreychuk. Daria, please respond to Professor Andreychuk's remarks.
Thank you, Professor Andreychuk, for your remarks. I agree with your comments, and I'd like to thank you for noticing some of my misprints or mismeaning, and about the threshold numbers, which was not so clear in numericals numbers, and I can show in the last chapter we add them. We demonstrate that the supermodes of the dimer split on the quartets, these quartets, for example, and under each quarter we denoted the threshold value, which is visible, which give us to see that all quartets has different values of this threshold. And if the number of the value of separation distance between the dimers, this L gets bigger than all our supermods for different colors here tends to the another value, but for single nanowire. So here you can see that some of supermods are lower in threshold value than maybe it should be presented in more details in dissertation. So yeah, I agree. Maybe it was something misunderstanding. And thank you for your reasonable comments. That's all.
Thank you, Daria. Professor Andreychuk, are you satisfied with the answers?
Yeah, I'm satisfied for this. Thank you very much. Thank you.
Yes, thanks. Then I am giving the floor to the first internal reviewer, Dr. Sergei Stishenko. Please.
Good afternoon, dear colleagues. Do you hear me?
Yes, yes.
1 week ago, we listened to the presentation of Fedor Yevtushenko. This research of Daria Gerasimova, together with that one, makes a significant contribution to the study of structures containing such modern material as graphene. While Yevtushenko considered the problem of scattering of a plane wave on strip gratings, Daria solved the problem of scattering of the electron beam field on nanowires. At first sight, this formulation seems to be a bit paradoxical because electron beam will just burn the nanowires. Nevertheless, this problem has a right to exist if beams with low currents are considered. Among the new results, I would select the detection of new resonances which occurs when the electron beam shifts from its symmetrical position. This effect is proposed to be used to determine the deviation of the position of the beam from its symmetrical one. I have a few critical comments. First, in my opinion, the thesis would benefit from cooperation with specialists in the field of vacuum electronics. In particular, this would make it possible to better formulate the practical significance of the research. The second, spatial charge waves of electron beam are not taken into account, but it was not difficult to do this. You just had to consider two terms in the presentation for your beam current. It is not, the third comment, it is not appropriate to use the term machine precision. It is not achievable in the problems under consideration. Even simple arithmetic operations have not machine precision due to register overflow. In addition, the error of the models themselves makes the pursuit of machine accuracy useless. There are some misprints in English and Ukrainian parts of the text, but I will not stop on them. These shortcomings do not reduce the overall positive impression of the work. To carry out the research, the candidate mastered complex mathematical apparatus, which includes the additional theorem and the method of analytical regularization. It is also worth noting the high level of journals in which the work have been published. I believe this research is a completed scientific work that contains a number of new interesting results, and it fully complies with all current requirements. And Daria Gerasimova deserves to be awarded scientific degree of Doctor of Philosophy in the field of knowledge, natural sciences, specialty physics, and astronomy. That's all. Thank you for your attention.
Thank you very much. Daria, please respond to the Dr. Stishenko remarks.
Yeah, can I answer? Yes.
Yes, yes, you can. Yes.
Thank you. Thank you for your reasonable remarks, Dr. Stishenko. Regarding, can add something regarding practical significance of the research here. In general, I agree with you. I have already discussed this matter with Dr. Kuleshov. And I think in our case, the diffraction radiation nanosize wires probably relates more to nanoelectronics with weak currents and with devices with weak currents. And about the term machine precision, as I said, it's used to underline the advantage of our code, and maybe I should modify this term. However, in our some paper, we have shown, let me show you, that the precise high precision can be reached with increasing and completion order for even different relative velocities of the beam. And that was this paper in journal that the topics of. And that's all, I think. Thank you for your comments and remarks.
Thank you, Daria.
I satisfied.
Okay, so thank you very much. Next, the floor is given to the second internal reviewer, Dr. Konstantin Serenko. Please go ahead.
Good afternoon, dear colleagues. As I'm the last to speak, I will not stop on what has already been said, like scientific novelty of the obtained results and their practical value. I'm gonna only highlight the points which are different in my review or seems of a particular importance for me. First of all, I would like to point witty way how a gap of knowledge was found by Daria in her dissertation. The topic of diffraction radiation is being studied for past 50 or even 70 years, if you count from the Smith and Purcell paper, but still she was able to find a direction which was not studied in details enough and built her work on it. Also, the use of graphene contributes to it, which is a new material and has and still has lots of to discover. Then, as it was mentioned, the result of the dissertation are published in an impressive list of high-ranking journals and presented at international conferences. And I was also impressed by the fact that 7 grants and awards were obtained during the PhD years of Daria. Next. And from it I could jump directly to my remarks and feedback on the dissertation. First, I would like to note that the application of the method of analytical regularization for derivation the equation which were solved numerically could be better referenced or documented, because the very few reference to previous papers where this when in section 2.2 and 3.3 during the derivation, it would be nice to see why and why we do those manipulation and where does it come from. Also, at points it was not sometimes completely clear where the previous result end and the new result start, like with adaptation of optical theorem. The most important remark is in section 3.3 and 3.3, where dimers are discussed as the potential of dimers is discussed to be used as beam position monitors. The presented results illustrate only two shifts of the beam, namely two positions of the beam, namely the central position between dimers, like 0 shift, and one shift value of 5 nanometers, if I'm not confused. But as the effect of beam shift in the focus of this part of study, it would be illustrative and instructive to consider other values of the beam shift. It would possibly give a picture how those resonances shift together with beam, like how they move, so to say, and discover the tendencies with respect to the electron beam shift. And in the version of the text I was reading, which I obtained before the previous seminar, there were a number of typos and some math notation and formula numbers and formatting issues, but there is a chance all those minor issues were fixed in the final version of the manuscript. In general, these remarks are mostly cosmetic, and I have a very positive overall impression of the dissertation, and its author, Daria, definitely deserve the award of the PhD title. That's all. Thank you.
Thank you very much. Daria, please respond to Dr. Sirenko comments.
Thank you, Dr. Sirenko, for your comments and remarks. Yeah, some mistakes was fixed before the last version of dissertation, and I can add regarding the variety of values of the distance of the beam from the x-axis. In the dimer case, there are two limitations. The allowed beam displacement is restricted by the separation distance between the wires, as the trajectory cannot cross the wire. Otherwise, the equations lost Fredholm type. And the separation should be not larger than the fraction of the wire's radius. Otherwise, the wires do not optically interact with each other, and the supermodes come together so closely in frequency that their peaks overlaps. And we had some investigation for the small range of displacement, and it showed that if the displacement the bigger, then the higher intensity of the peaks of new resonances. And yeah, about everything else I agreed, and thank you for your comments again.
Dr. Sirenko, are you satisfied with answers?
Yes, absolutely. Thank you.
Thanks. I noticed that the most reviewers combined dissertation, discussion, and so evaluation process. But now please, I would like every jury member take part in the discussion to tell something about dissertation. Please, who can start? In general, this means you are giving your evaluation of the dissertation. Totally, maybe you would like to turn attention to some results, but please do it very briefly. Who will start?
Okay. Can I
Yes, okay.
be first?
Please start, yes.
Okay, Daria dissertation is another work in the family of dissertations carried out by the team led by Alexander Nosit, which is distinguished by high-quality scientific style and attention to detail. I would like to say thank you to Daria's team for inviting me as an opponent. This allowed me to expand and deepen my scientific horizons, and I will vote for awarding Daria Gerasimova a PhD degree. That's all.
Okay, thank you very much.
Thank you.
Please, other jury members, please start. Who is next? We cannot hear you. Professor Andreychuk, please switch on your microphone.
It is very impressive results about the topic on the investigation. It is a very big number of numerical data, and it is the second step to use this result in the practical application, and very nice publication in the journal. And in my opinion, it is a very good first start for the doctor science degree. I wish all success in the scientific works and all the best in life. Thank you very much.
Okay, thanks a lot. Who else?
Thank you.
Thanks, Professor Andreychuk. Please, who else?
I can say a few words. Daria, as you, I discussed your dissertation with Alexei Kuleshov, and he proposed an interesting application of your results. I think he told the same to you. According to him, it is possible to use your resonance found by you, resonance, to arrange the position of electron beam at the first stage when the current is low. And further increasing of current, of course, it will burn the nanowires, but it will not change the position of electron beam. So your result can be used even in vacuum electronics. I would say that you made a good presentation, and we heard your answers on the questions. So of course, you showed your level of qualification, and I will vote yes.
Thank you.
Okay, thanks. Dr. Tserenko.
Yeah, now it's my turn to say a few good words. So yeah, this is a very good dissertation, and I'm glad I was invited to be the reviewer of this one, and the one was defended a week ago. I have a very positive impression of the manuscript itself. It's well written and interesting to read, and also the Daria's presentations today and at the seminar confident and definitely show her as a person which deserves to be a PhD. So yes, I definitely support the award of PhD title to Daria.
Okay, thank you very much.
much.
And I would like also to tell something. The report, Daria, your report was good. Results are impressive. Maybe my comments that when you compare your results with commercial software, I would extend this. I would, for example, take another commercial software, namely three-dimensional, to show how your resonance frequency will be affected by the dimension, the size of your cylinder in that direction. It would be interesting. It would be interesting to compare. So because you did 2D case, but some of the present is from audience asked a question about so your problem. Of course, you solved vector problem, but two-dimensional. But vector, no doubt that it's a vector problem. It's not scalar. It's a vector problem. So I would so I would compare with the three-dimensional case to show how your resonances are affected. So in general, I asked you about why did you choose electronic beam excitation instead of plane wave? You answered it's a question of symmetry, because yes, you answered that it's another symmetry. Yes, I agree with this. I asked about regularization procedure. I understand that you are worried so much, but you answered particularly. But in general, it depends. It is connected with the matrix element behavior along, for example, columns and
Lines.
Yes, and lines. So, and probably in your regularization, you took into account this, and now your behavior is in this direction, in these two different directions, is very good to be how to say, to imply regularization procedure. But nevertheless, I am impressed by your dissertation, and no doubt for me that you deserve to have PhD degree.
Thank you very much, Professor Sezhentsev, for your comments too. Yeah, it was nice to have you here leading this.
Now I would like that your scientific supervisor, Dr. Sergei Dukhopelnikov, maybe he wants to tell something. Please.
Yes, thank you. Good afternoon, dear colleagues. I would like to note not only Daria's skills in solving difficult problems, the solution of which have been published in high related international journals, but also her ability to present her results. Because participation and the successful presentation of results will be a very important part of the development of Ukrainian science. Therefore, I wish Daria not to stop at what she has achieved, but to continue with the same diligence. And of course, I think that her work deserves a PhD degree. Thank you.
Thank you.
Okay. Thank you very much. Daria, please, you are given the final word.
Okay. Do you hear me?
Yes.
Yeah, okay, thank you.
Yeah, please start.
So yeah, thank you for giving the word. First of all, I am grateful to all jury members for their time and professional opinion. Then I'd like to thank Professor Nosic and Dr. Dukhopelnikov for their encouragement and guidance, Professor Cherpak for the support, and all Institute's colleagues for the work they are doing in Kharkiv in these challenging times. I really appreciate the participation on Professors Shepkovich and Dazdemir. Thank you. Also, I'd like to express my huge gratitude to the Ukrainian Defense Forces for the possibility to work and live in our independent country. Thank you, Slava Ukraini.
Okay, thanks. Excuse me, I drop. Excuse me, I drop some process, some step over the process. Are there some foreign participants who wants to tell something, please.
Yes, if I may. Yes, I consider Daria's work really impressive, and the 6 papers published in international high-rank journals are important also for the foreign community to see this quality of Ukrainian science. So I looked at some of these papers. I also noted that these, for example, paper number 6 was cited in a recent publication in Physical Review A. It was cited in June last year. And this is a publication by Haller and Schachter, and they consider a 3-dimensional problem, which of course is much harder. And it's interesting because also in addition to scattered radiation, you have radiation inside the rod, which propagates along the rod. But Daria, the strength of your work is also in the consideration of an array of rods, which I didn't believe it can be treated analytically. So it's really impressive. And this work that cites you is only for a single rod. And I'm not sure if anyone will ever do it for an array of 3-dimensional rods. I think it's super hard. But so it's a strength of, maybe this is a simple 2-dimensional model, but you treat an array of rods, which is very valuable. Yeah. Okay, thank you.
Okay, yes, thank you very much.
Thank you very much.
Who else from foreign participants wants to tell something? No people. Okay, now I will go. We will go to final step. I will start in this step in Ukrainian. Переходимо до голосування щодо присудження Герасимовій Дарії Олександрівні ступеня доктора філософії. Голосування відкрите підняттям руки. Хто за? Прошу голосувати. All jury members. Окей. Хто проти? Немає. Хто утримався? Немає. Результати голосування за присудження Герасимовій Дарії Олександрівні ступеня доктора філософії проголосували 5 членів Ради. Усі. Шановні колеги, вам заздалегідь було розіслано проект рішення Ради про присудження ступеня доктора філософії Герасимовій Дарії Олександрівні. Переходимо до обговорення. Є зауваження або коментарі щодо проєкту?
Нема.
У мене нема.
Немає. У мене теж немає. Таким чином оголошується рішення Ради щодо присудження здобувачці ступеня доктора філософії. На підставі результатів відкритого голосування спеціалізована вчена рада присуджує Герасимовій Дар'ї Олександрівні ступінь доктора філософії з гаузі знань 10, природничі науки за спеціальністю 104, фізика та астрономія. Дар'я Олександрівна, вітаємо вас з успішним захистом дисертації. Бажаємо успіхів у подальшій роботі.
Дуже дякую.
Also, I would like to thank scientific secretary of our institute, Кривенко Олена, and manager of specialized scientific council, Tapchi Marina, for help to organize this PhD defense. Thank you to all participants, especially to foreign participants. My all best wishes to all of you. Дуже дякую. До побачення. Ми завершимо.
До побачення.
Будьте здорові всі, до побачення, всього найкращого.
До побачення.